Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that useless hate energy into useful love energy. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. In this video series on algebra, we'll be discussing a tool. It's really a tool. Algebra is just a tool for doing higher level mathematics. And it's a very important tool because without it, we wouldn't be able to do very much. And essentially, algebra deals with expressions that involve variables or letters representing numbers. Their variables are really placeholders for numbers, and we use all the bedmass rules and all sorts of properties in order to simplify really complicated expressions. Why do we need to simplify these complicated expressions? Because when they're in complex form, they're very hard to analyze, very hard to interpret. But when we reduce these complex forms using algebra to something simple, then that simple expression is readily analyzed. And if we're in the middle of doing a physics problem or some problem in science or engineering, in reduced form, that expression would be much easier to analyze. The mathematics starts actually talking to us. But in expanded form and unsimplified form, it's very hard to analyze. Basically, it consists of two parts. One part is learning how to expand and collect like terms. And the other part, which is much more difficult, is learning how to factor, which is essentially the inverse procedure for expanding. It's quite straightforward to factor or to expand. Although it can be very tedious to expand, the procedure is very straightforward and you can become very good at it. The inverse process, which is called factoring, requires a lot more thinking. You've got to be quite ingenious in order to execute some factoring problems. Anyway, without further ado, we'll go on to slide 1. Let's look at question 1 over here. It says expanding and collecting like terms, which I abbreviate to CLT, using backward bin gathering, BBG. The notion of backward bin gathering was introduced in the bedmass series, so I would urge you to go back to the bedmass series and look at some of the backward bin gathering that we were doing there. But even if you don't do that, you'll pick it up on the fly, I'm sure. Let's look at question 1a. If you look at this carefully over here, we have a set of brackets here, a set of brackets there, a set of brackets there. The separators are a plus sign and a minus sign. Inside the brackets, this is like an additive string. They're not multiplying, they're adding. But because we have the set of brackets over here, we'll call this a cluster. Again, we have an additive string over here. Because of the brackets, we'll call it another cluster. And again, we'll call this another cluster, even though it's an additive string. If we look at each cluster, or the contents of each cluster, we notice that we have 3 terms. That's called a trinomial. And we'll notice that the highest power of the variable x is 2. And that's called the degree of the polynomial, or the trinomial. In this case, it's a trinomial, but we can have much longer expressions, which we will then call polynomials. Whenever the degree is 2, we call the expression a quadratic. And of course, we have a quadratic here, quadratic there, quadratics right across the board for each cluster. So the idea is to combine these clusters and to obtain a simpler expression at the end. Okay, so we identify 3 clusters, and we'll be using backward bin gathering in order to simplify this little mess that we have up here. The first thing you do is look at the highest power, which is x squared. we open up an x squared bin and make the bin empty. We will go across over here, we'll scan across the entire expression and only focus on the x squared terms. Over here the coefficient is 7, we drop it inside the bin. The coefficient is 9, we'll drop it inside the bin. The coefficient of the x squared term over here is really minus 4. You can distribute the minus sign visually. There's no need to go through an extra step distributing that because it's very easy to do. And so we drop the minus 4 inside the bin, close up the bin. There are no more x squared terms. Though we open up a plus bin, or sorry, a plus x bin. Always a plus sign in between the bins. That's a part of the process of BBG, is using plus signs in between the bins. Never a minus sign, you'll begin making sign errors. So we'll open up a plus x bin. Of course, x is called a linear term because it's x to the power 1. So we'll scan the expression only for linear terms. We pick up a negative 2 here, drop it inside the bin. Pick up negative 4, drop it inside the bin. And we pick up a minus 6, drop it inside the bin, and we'll close the bin. Then we open up a constant bin. The constant bin, the label outside the constant bin, you don't see any label at all. That's because the real label outside the bin is x to the power 0. And x to the power 0 is 1, and 1 times anything is just that anything. So we put nothing out front. But this is really an x to the power 0 bin. Let's scan for constant terms. We pick up a 1 here, we pick up plus 5 here, and minus 7 is plus 7. The idea now is to simplify inside each bin. We get 7 plus 9 minus 4 is 12. And so we write down 12x squared, and minus 6 minus 4, or sorry, minus 2 minus 4 minus 6 is minus 12x, and 1 plus 5 plus 7 is 13. So at the end over here, we have a trinomial. The degree is 2, and the coefficients are 12, negative 12, and 13. So this we declare to be the expanded form of the original expression. Much easier to analyze this than to analyze this in raw form. Let's go on to part B over here. And if we look at this carefully, we see a set of bins, or a set of brackets here and a set of brackets here. With a separator, the separator between the brackets is a minus sign. So essentially we have two clusters. Each cluster contains two variables, a and b. If we look at the highest power appearing is 2. So we call this a trinomial of degree 2 in two variables. Okay, or you can use the term, it's a quadratic polynomial in two variables. So this is quadratic in two variables, and this is quadratic in two variables as well. And the idea is to join up these two quadratics together to form a more simple quadratic. And we're going to use backward bin gathering to do that. We start by opening up an a squared bin. So you do a squared dot empty bin. We scan, we drop in a 7, and we drop in a minus is plus, so we drop in a plus 1, and then close up the bin. The next bin will be a plus AB bin. So we put down plus a dot b, empty bin. We scan the expression only for a dot b terms, so we get negative 4 here is the coefficient. We get minus 2 over here is the coefficient, drop it inside the bin, and then close up the bin. The last bin will be the b squared bin. So we put a plus b squared dot empty bin. We scan, we pick up a 9 here, we pick up a minus 6 here, and we drop it in. At the end, we simplify inside each bin. So we get a 7 plus 1 is 8. We get 8a squared. And minus 4 minus 2 is minus 6. So we get minus 6a dot b. And 9 minus 6 is 3. So we get a 3b squared. So at the end over here, we have a trinomial in two variables. The degree is 2. Okay, so it's a quadratic polynomial in two variables. So this looks much simpler than the original. Let's go on to another slide. Question 4 is on expanding and collecting like terms using backward bin gathering. So it's the same sort of thing. The basic difference here is that we're going to be multiplying. If you look at this expression carefully, you see a dot here, dot here. So we only have one cluster over here. And it's a multiplicative cluster this time. The other one was an additive cluster. The other questions that we were doing were additive. This is multiplicative. The minus 3 is an external coefficient. We're just going to leave it alone. Over here, we identify this as a bullet, another bullet, and 2 targets. So 2 bullets and 2 targets. And what we're going to be doing is start firing bullets at targets. When you fire a bullet at a target, it's always multiplication. Okay, well, so when a bullet hits a target, the operation is multiplication at all times. So we're going to put a hold on the minus 3, and we have 2 bullets dotted with 2 targets. And this bullet, target, target procedure over here is really the distributive law. Okay, I just call it bullet, target, target because it makes it easier for people to execute properly. All we're doing is firing bullets at targets, and that's really called distribution. So the minus 3, we're going to do a drop down. We're going to fire the first bullet at both targets. We have a 7x dot 4x is 28x squared, put it down. 7x dot negative 7 is minus 49x, put it down. And we've exhausted the first bullet. The second bullet's negative 5. We're going to fire this bullet at both targets. We get minus 5 dot 4x is minus 20x, and minus 5 dot negative 7 is plus 35. Now the idea here is to collect like terms inside the brackets. So that's what we'll do in the next step. The minus 3 is just a drop down. That's the external coefficient. And the 28x squared drop down. There are no other terms in x squared. And minus 49x minus 20x becomes minus 69x. You just add the 2 terms because they're like terms. 35 is just a drop down. At the end over here, you see a single bullet on the outside, and we see 3 targets. So we're going to launch this bullet and hit each of the 3 targets. So minus 3 dot 28 is minus 84 dot x squared. Minus 3 dot minus 69 is plus 207 dot x. And minus 3 dot 35 is minus 105. At the end over here, this is our final answer. We have a trinomial in one variable of degree 2. So this is called a quadratic polynomial. Okay. This is called the factored form, and this is called the expanded form. And believe it or not, the factored form is a more useful form than the expanded form. Often questions in textbooks will say simplify instead of expand. You're not really simplifying when you're expanding. Okay, as a matter of fact, you're killing the problem. In factored form, we can obtain information that you cannot obtain readily from the expanded form. The moral of the story is, if you don't need to expand, don't do it. Don't do it. Whenever you expand, you have to expand with a purpose. If there is no purpose in expanding, do not do it, because essentially you're killing the mathematics. You're going against the grain. Okay, the mathematics is trying to help you out, and you're destroying it. And eventually the math will give up on you, and then you'll be thoroughly lost. And in the background, the math is really saying, I told you so. Anyway, word of caution, only expand when it's necessary. Do not expand arbitrarily with no reason. Anyway, we'll go on to the next slide. This is a similar sort of problem, a little bit more complicated. I see a dot in between the brackets over here, so I declare this whole thing to be a single cluster. And this term over here is an additive term. This is an additive term, but the dot over here indicates the entire thing will be a single cluster. The minus sign out front is really -1, and it's an external multiplier. Leave it alone for the time being. Okay, it's going to be a drop down until the very end. It's not doing anybody any harm. Just drop it down. Over here, we identified 3 bullets and 3 targets. This over here is a quadratic in y, and this is also a quadratic in y. It's degree 2, degree 2. If we look at only the leading terms, which are the terms of highest power, we get a y squared. And over here we get a 3y squared. If you multiply those together, you get a 3y to the power 4. That means when we expand this, we should get a polynomial of degree 4 at the end, okay? So that's how you know what the degree of the polynomial is that you'll get at the end before you even start expanding. Just look at the leading term and the leading term, multiply them out, you'll get 3y to the power 4, and you know for certain that the polynomial that you'll get at the end will be of degree 4. We're going to put a hold on the -1. That's the external coefficient. And we'll notice we have 3 bullets and 3 targets. And we're going to launch each bullet at each of the 3 targets. So the minus sign comes down. When we launch the first bullet, we get a y squared dot y squared, which would be 3y to the power 4. And then y squared dot minus 5y, which will be minus 5y cubed. And y squared dot -3 is minus 3y squared. And we've exhausted the first bullet. Second bullet, minus 4y dot 3y squared is minus 12y cubed. Minus 4y dot minus 5y is plus 20y squared. And then minus 4y dot -3 is 12y. And we've exhausted the second bullet. Now we'll turn our attention to the third bullet. 7 dot 3y squared is 21y squared, and 7 dot minus 5y is minus 35y, and 7 dot -3 is minus 21. So we have a fairly horrendous looking expression in here, but not really. Okay, it just looks bad until we compress it. Again, the minus sign becomes a drop down. Actually, I decided not to drop it down this time because a minus sign is easy to deal with. If I distribute the minus sign right across the board over here, the minus sign simply serves to do a sign change for each term right across the board. So all the minus sign does is change the sign of each term. And that's what I did. So I get a minus 3y to the power 4 plus 5y cubed plus 3y squared plus 12y cubed minus 20y squared minus 12y minus 21y squared plus 35y plus 21. And now it's time to collect like terms using backward bin gathering. I start by looking at the term of highest degree, which is y to the power 4. So I open up a y to the power 4 bin, scan the expression for all the y to the power 4 coefficients. We only pick up -3. There are no more y to the power 4 terms here. So we close up y to the power 4 bin. Then next, plus y cubed. Notice a plus sign in between the bins. Plus y cubed dot empty bin. And then scan the expression for y cubed terms. You pick up a 5 here and a 12 there. Drop it in, close up the bin. There are no more y cubed terms. Then plus y squared dot empty bin. Scan for y squared terms. We pick up a 3, drop it in. We pick up -20, drop it in. Pick up -21, drop it inside the bin. Close up the bin. Then a plus y empty bin. And we scan for linear terms. The linear term here is -12, drop it in. And the linear term here is plus 35, drop it in. Close up the bin. Lastly, we open up a constant bin. If you scan the entire polynomial over here, you only pick up one constant term, which is 21. At the end, all you have to do is simplify the expression inside each bin. Minus 3 just becomes minus 3y to the power 4. 5 plus 12 is 17, so we write plus 17y cubed. 3 minus 20 minus 21 is minus 38. So we write minus 38 dot y squared. And minus 12 plus 35 is plus 23 dot y. And then plus 21 at the end. So now this is nice and neat. We have a polynomial of degree 4 in one variable, y. Okay, so this is called a quartic polynomial in y. Degree 4 means quartic. Degree 2 means quadratic. Degree 1 means linear. Degree 3 means cubic. Okay, now this was the sort of factored form that we started out with. And then essentially we used backward bin, or we used the bullet target method, or 3 bullet 3 target method over here. I just call it the bullet target method. Regardless of how many bullets, how many targets there are, I call it the bullet target method. We use the bullet target method to expand everything, and then we use backward bin gathering to collect like terms to get this quartic polynomial in y at the end. But again, factored form is actually more useful than the expanded form. Okay, so we'll get into that in other videos to come. I think we're going to do an over and out at this point. Okay, thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from MathLab Tutorials in Toronto.